Thank you very much to the presenters and the audience for being here today. This is our third doctoral meeting session. It's a quite exciting session on again, electric propulsion for space environment. And we'll be having today 7 presentations by Maria Sherezade, Celia Amboyé, David García-Lahuerta, David Madaloni, Víctor Gómez García, David García Villegas, and Borja de Saavedra. Basically, we're going to be today listening to 3 presentations on the Zarathustra Starting Ground project that Mario presented to us in March, and you have the presentation and the recording should you want to check what he's proposing. So it will be a good opportunity to listen to his project. Maria will be presenting her thesis on micropulse plasma thruster design. So again, an experimental PhD thesis, very interesting one. And then we'll be hearing to 3 industrial PhDs with CENER and ENI Space. ENI Space indeed is a spin-off of some research that was done in EP2 group 2-3 years ago. So it's very interesting also to see what we are being able to transfer to society in the form of a spin-off and new positions for people and groundbreaking research. As you know, the presentation should be 10 to maximum 15 minutes long, right? So keep an eye on the time. We will be strict on the time, right? Because then we'll need some minutes for questions. Right.
Okay. So, hi, I'm Diego Garcia. Thanks for having me in the doctoral meetings. I'm gonna present my PhD thesis, which is also framed in the project of the Zarathustra project. My PhD thesis is called Modeling of Advanced Electrodeless Plasma Thrusters. And it's supervised by Professor Mario Merino and Professor Eduardo Aero. So to begin with, I'll talk a little bit about the contents of the presentation. So I'll give it first a fast motivation. Yeah.
Sorry, if you are moving to now, okay. Now we have the second slide. Okay, I don't know if you.
Okay.
Now we have the first slide, before not. Now.
Okay. Yeah, I don't know why it was not working. Okay. So yeah, I'll talk a little bit about the magnetic arc thruster first, but not so much because already Celian talked about it. Then I'll talk about the thesis objectives and about the methodologies I'm using, the model, and the integration method I'm using. That's the discontinuous Galerkin method. And then to finish with, I'll talk about the next steps we will take in the thesis. So first of all, the motivation is the magnetic arc thruster, which is the design that Mario proposed, and that is the main object of study of the Zarathustra project. So as Celian said, it promises this model design you said promises some advantages compared to traditional EPTs. Mainly the reduced wall losses due to the lack of a back wall, and the reduced plume divergence, and also the reduced dipole moment of the thruster. But with these advantages also come some challenges for the simulation of this kind of thruster, which is that the problem is now fully 3-dimensional, so we don't have an axis symmetry. That's going to make the computations more expensive. And also we have a quite complex magnetic geometry, so we expect, as I'll talk about it later, we expect the appearance of compression waves and shock waves and many other features. And also we don't know if the operation of the thruster will be stationary, so we have to take care of that. Then let's go on with the objectives of the thesis. The main objective of the thesis is to understand the physics of the magnetic arc thruster while doing models and solving them numerically. We want to pay special focus at the moment to the external part of the thruster. So we are going to study the expansion of the bloom in the magnetic field. And we also want to calculate afterwards the plasma-induced magnetic fields and to study the problem of the detachment of the plasma from the magnetic field. Also, englobed in this major objectives of understanding the physics of the magnetic arc thruster, we want to produce a complete fluid code for the simulation of electrodeless plasma thrusters. So let's go on with the methodology. The model we are using, as Elian said before, is that the magnetic arc thruster consists of two magnetic nozzles with opposing polarities. And as I said before, the geometry is going to be three-dimensional. Here we have a depiction of the applied magnetic field, of the streamlines of the applied magnetic field. And we are expecting the plasma-induced magnetic field to have a bigger role in the total magnetic field. So we expect to have a quite complex total magnetic field where we may have zero field regions and even reversed field regions. This is a depiction of how we expect the magnetic field, the total magnetic field, to look like. Also, another feature that the thruster is going to have is that we have two ion streams coming out of each nozzle. So we're going to have an interaction of the magnetic of the ion streams at some point. We are expecting the interaction of these ion streams to produce a compression wave, which may lead to shock waves and other features. And we are expecting to have supersonic regions or subsonic regions and many other features in the outside part of the thruster. And also, as I said before, we expect the operation to be, we may have a non-stationary operation. So what's the model that I am using right now for the plasma? I'm using a two-fluid model, which is the simplest model we can use to understand the major physics of the thruster. So we're using a quasi-neutral collisionless plasma and massless isothermal and fully magnetized electrons. With these assumptions, the electron equations are found to be algebraic, so we only have to integrate for the ion equations, basically, which are considered the ions cold and singly charged. And as you see here, we have a time dependent time dependency in the equations. You may find that these equations, the ion equations, are very reminiscent of the compressible Euler equations of fluid dynamics. And let's go on then. What are we using to integrate the ion equations? We're using the discontinuous Galerkin method, which after a review of the state of the art, we have found that will be a very suitable method for the integration of the problem. We'll talk a little bit later about what's exactly the discontinuous Galerkin method, but why did we choose it? Basically, it offers some great features, mainly that is local, even in high order methods. Also, it's a conservative method, and it offers the possibility of having HP adaptivity, which is basically that we can refine our solution both by refining the mesh and by refining the order of the polynomial. And it offers great support for complex geometry, so we can use unstructured meshes with meshes, which will be a great feature for the complex magnetic field that we're going to have. And also, it offers a great feature that it's going to give us a lot of flexibility for the time-stepping procedure. And it's the fact that it offers a semi-discrete form so that you can discretize in time afterwards with explicit schemes like strong stability preserving Wunderputta methods, or even implicit schemes if we don't find a suitable time step. Here, which is not shown, but is the typical solution of an advection problem with discontinuous Galerkin in one dimension, obviously. So we go on. Let me see. Yeah. So what's exactly the discontinuous Galerkin method? The discontinuous Galerkin method is a finite element method with some traits from finite volumes. We basically discretize our domain in K cells and assume that we have a local solution described by a polynomial. But the difference with common finite elements is that we don't assume continuity at cell interfaces. And then we enforce, as usual, as is customary in finite elements, we enforce the satisfaction of the conservation law by weakly through the multiplication by these functions. And the part where finite volumes come is that we have to use a numerical flux to approximate the physical flux between the cells because we are allowing discontinuities to appear in the cell interfaces. Here, you also have a depiction of what a typical solution in discontinuous Galerkin method looks like, where we have at each cell, we have the description of the solution by a polynomial, but we are allowing discontinuities at cell interfaces. And here are the basic equations that you find for these discontinuous Galerkin methods. Okay, so right now we are using the Phoenix project to solve the discontinuous Galerkin problem. And we have checked the convergence of the compressible Euler equations using manufactured solutions to study how the discontinuous Galerkin works in our case. And we have obtained a suboptimal convergence rate of order p of the order of the polynomial. Here I had a GIF of the solution of the subtip problem in discontinuous Galerkin, but we can't see it in this presentation way. But let's go on. And to finish with, let's talk about the next steps we're going to take. And basically, we have to include the right-hand side of the ion equations that appeared in the sixth slide. The next steps afterwards will be the calculation of currents in the plasma and the maps of the plasma properties to afterwards include the plasma-induced magnetic fields. And then we want to compare our results with known results for axisymmetric nozzles. And then afterwards, we want to extend the software to solve 3D problems and go to the main problem, that is the magnetic arc thrust. So this is basically all. As I said, my thesis is framed in the Zarathustra project. And thank you very much. So if there are any questions,